So thank you very much. It's really a pleasure to be here. Dr. Hazen made the point that the new appreciation of the microbiome is a lot like the discovery of a new endocrine organ, and I really appreciate that comment. And so that's a big game changer, because we now have thousands of bugs producing many, many more metabolites and responsible for a lot of physiology. And the magnitude of the problem was presented by Dr. Relman this morning when he said we're outnumbered 150 to 1 in DNA, 10 to 1 in the organisms, and it's going to be much greater than that in the metabolites, which are, in Stan's way of putting it, the hormones. So then the question becomes, how do we piece it all together? How are we going to figure out the line of causation, and I'm extending the causation issue, to understand what organisms and what products of those organisms are responsible for modulating particular biochemical and physiological pathways. And there's a limit to what we can do with hypothesis testing science, which we all think of as the most rigorous science, and that's that the most rigorous experiment tests only one variable at a time. And so if you do the math, you have way too many variables to be able to test in one lifetime, or certainly under one NIH grant. So what I want to do is just say a few words about how we can approach this difficult problem of too many variables and an intense desire to establish causality. And so I have a few simple slides. That are not advancing. Here we go. And so here's the question that's posed, and that is, what is in those arrows? What is in the arrows that link the host cells with metabolites, with microbes? So microbes are interacting with the host cells, and there are obviously a lot of host cell differences that make one population have different microbes than others, or one mouse strain have different microbes than others, and then the metabolites that they produce. Okay, so here's the issue. What's going to happen now is investigators who are gaining an appreciation of this field are going to take a census of what microbes are in their model organism or the human subjects. It'll become commodified like many other omics technologies have, and so they'll be able to carry out these studies and get a lot of data back on organisms. There'll also be the same thing happening on the metabolomic front. There'll be a tremendous amount of data generated on the metabolites that inhabit the gut or are circulating in the bloodstream. And so what you can do with this data very easily is tell the computer to calculate pairwise correlations. And when you do that, you get many, many correlations that are very high, very strong correlations. The problem is that most of these correlations are not causal. And the challenge then is to sift through that and discover which, from among the many correlations, which few are truly causal. That's the challenge, and that's really, really tough. So for example, if you have A and B correlated, A and B could be an organism and inflammation, or a metabolite and risk of heart disease, like Stan was talking about. That correlation could be causal, or it could be because some external agent X is acting on A and B in a coordinated fashion, so it looks like A and B are correlated in a causal fashion. But there's no true causation there. I don't know where I'm supposed to point. There we go. And so, but the other thing that can happen is that there truly is causation. A could be affecting B, or B could be affecting A. And the question is, how can we discover that? What are we going to do to discover that? I realize what's happened here. It's you know, I'm going to skip the slides. I'll wave my arms. No, it's okay. I can live without slides. So the issue then is a little bit like having a stack of punch cards, a very big stack of punch cards. And you want to insert a rod through those punch cards and discover which cards have their holes aligned. That's pretty simple to do. And the question is, how can we do that in biology? And I'm going to argue that genetics allows us to do that. Because what happens in genetics is you have a bunch of factors, we'll call them host factors, that are shuffled by Mendelian randomization. And so in an outbred population like the human population, you have all this shuffling that has occurred. And hence you have the stack of cards with some holes aligned and some not. But the relationship between a genetic variant and a phenotype is truly causal. That's non-negotiable. That is true, and we can live by that. And that is incredibly useful for this kind of biology, because we can use that as an anchor point. We can say that a gene variant is not correlating with a phenotype, it's causal for that phenotype. And then we can build a model that emanates from that. And so, so one of the approaches that can be used in model organisms and in human populations is to include genotyping data, and then to do all the omics modeling that you do. You can do metabolomics, you can take a census of the microbiome, and you can do transcriptomics, and then begin to order these things into defined pathways. And so this is one approach that I hope people will begin to adopt to an enormously complex and absolutely fascinating problem that has emerged from a real game changer.
Okay, thank you very much.